In this video, we'll talk about colors. A good design should work without any colors, and this is the reason why we used only gray in the mockups. However, color is one of the first elements of the design that will be perceived by the user, and therefore it plays a big part in the aesthetic perception of the design. Color is also very useful to improve balance and hierarchy. Choosing colors effectively requires you to understand the basic concept of color theory, color schemes, and to have a good overview of color meaning. This will allow you to create a consistent color palette for the app. But before we get to that, I found it very useful to understand how a color picker like the one in Sketch works. So let's start with that. Okay, first things first. Color perception is a component of visual perception, or sight. And visual perception is the ability to interpret the surrounding environment by processing information that is contained in visible light. It is basically the result of the encounter of light and a functioning eye and brain. This means that color, like everything else we see, is an information contained in light. And light can be reflected by an object. This is what happens when you see an apple, the fruit, or generated by an object, like the screen you're currently looking at, which can be on an Apple computer. And depending on the case, colors are formed differently. In the first case, with the fruit, we'll talk about subtractive colors. And in the second case, with the screen, we'll talk about additive colors. So let's start with subtractive colors. Physical objects, when struck by light, will reflect back certain wavelengths of light to your eyes. If pure light hits an apple, all colors are absorbed except for red. Red is the only color reflected back towards you, and therefore it is the color you attribute to the apple. It is the same thing with paint or ink. Pigments in the paint subtract wavelengths from the light. And the color that a painted surface displays depends on which parts of the visible spectrum are not absorbed and remain visible. The primary subtractive colors are cyan, magenta, and yellow. And logically, when you mix all the colors, the entire visible spectrum of the light is absorbed, and this gives us black, which is the absence of light. On the contrary, monitors' displays generate their own light. Colors are created by mixing light of two or more different colors. That's why we call them additive colors. Each pixel of your screen is composed of a red, a blue, and a green subpixel. Every color displayed on your screen is therefore created by mixing these three colors in various quantities. Red, green, and blue are the three additive primary colors. This is the reason why we use the RGB color model when dealing with colors on digital screens. I'll show you what I mean. Open a new sketch file and draw a square. You can select the shape here, or you can just hit R. Hold Shift and drag. The size of the square doesn't matter, but make it big enough so you can see the changes. Let's get rid of the border. That's it. Now click on the fill right here, and you should be able to see the color picker with the three letters RGB. If instead you have HSB, click on one of these letters. I'll explain later what these HSB letters correspond to. Alright, R stands for red, G for green, and B for blue. So, if we enter 0 for each of these values, can you guess what color will be displayed? Yes, black, that's right. Do you see why this makes sense? We're dealing with additive colors here, and additive colors are created by mixing light, and the three primary light colors are red, green, and blue. If we don't have any red light, green light, or blue light, then we don't have any light at all. We have darkness, we have black. The intensity of each color ranges from 0 to 255. This is the range that a single 8-bit byte can offer. Therefore, 255 of red is pure red. And if we add 255 of green, can you guess what color we get? Yes, yellow. Now let's add 255 of blue. And of course, the result is white. If zero intensity for each component gave us the darkest black, it makes sense that having all three colors at full intensity gives us white. You might have noticed along the way that the hex value over here changes each time we change the intensity of the colors. This hex value is made of 6 hexadecimal numbers. A hexadecimal number is a value between 1 and 16, represented by a number or letter from 0 to F, 0 being the first value, 9 the 10th value, A the 11th value, and F the 16th value. Each color intensity is represented by two hexadecimal numbers, 00 being the smallest intensity and F being the strongest. The combination of these two hexadecimal numbers allowed to cover the 0 to 255 range of intensity variation for each primary color. So a little bit of red, 1, a lot of green, F, and some blue, A, will give us this color. The Xcode of a color is often used on the web to refer to the color and is widely used in the design world as well. But this RGB model we just talked about can be a bit unintuitive when it comes to creating more complex colors. For instance, how would you create dark orange? It's a bit hard to guess the quantity and intensity of red, green, and blue you should add to obtain such a color. This is why the HSV or HSB model was invented. These three letters refer to three-handed concepts that allow a more intuitive definition of color. H stands for hue. It is the most basic of color terms. A hue is a color in its purer form. When we refer to colors like red, blue, yellow, orange, we're usually talking about hues. The value of the hue ranges from 0 to 360, and as you can see on the hue scale, it starts with red and it ends with red. This is because the classic representation of hues is a wheel. On this wheel, the primary additive colors, red, green, and blue, are located at the corners of an equilateral triangle. Therefore, the value of red is 0 or 360, which is the same thing. Green's value is 120, 1/3 of the perimeter away from red, and blue's value is 1 more third of the perimeter further away, so it is 240. So let's go back to our sketch file. Make sure you select the rectangle. Click on one of these three letters, RGB, to toggle to the HSV model. We'll write 100 in the S field. So 360 or 0 will be red. If we type 120, we should get some green. And 240 will be normally blue. Make sure you have 100 in the other fields. You don't have to know these numbers by heart. The hue scale over here allows you to select the colors easily. Next letter of the HSV or HSB model is S. S stands for saturation. Saturation refers to the purity of a hue. The more a color is saturated, the closer it will be to the pure hue. The less it is saturated, the closer it is to white. We can add this dimension to the color wheel. We'll have the desaturated colors in the center and the fully saturated colors on the border. Saturation can sometimes be represented like that, with fully saturated colors at the top and desaturated colors at the bottom. In Sketch, saturation is the x-axis of this color picker. Saturation ranges from 0 to 100. That corresponds to the percentage of saturation of the color. So here's the fully saturated red, and if we go down, you can see that the red square is less and less saturated. You can also see just over here that the picker is moving from right to left. Finally, we have the V or B, which stands for value or brightness. Brightness is a measure of the amount of light reflected from a color. It is basically how light or dark a hue is. This adds a third dimension to the model. And this cylinder is a complete geometric representation of the HSV or HSB model. But don't worry if this isn't crystal clear. What's important is that you understand how the color picker works. The cylinder doesn't really matter. So let's go back to Sketch and play around with the brightness. In Sketch, brightness is the y-axis. Unlike saturation, Brightness values range from 0% to 100%. As brightness goes down, the square's color gets closer to black, and the picker moves along the y-axis, like this. You might be asking yourself what this last A field means. This stands for alpha, and it sets the opacity of the color. If we place, let's see, a blue square, behind the red square, and that we change the opacity of the red square, we should be able to see the blue square behind, like this. Maximum alpha, which means full opacity, is 100%, and minimum alpha, which means total transparency, is 0%. Alpha is independent from the HSB or the RGB model. This is why it stays here when we toggle from one model to the other. The whole point of this lesson was to make you understand how the color picker works. I've tried to make it as simple as I could, but if you find it too technical, don't worry, this won't prevent you from using it and from understanding what follows about how to choose colors. Your homework for this lesson is to play this game about colors. Go to color.method.ac. And that's it.